Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. We are going to continue with chapter 4. So in the previous video we have discussed on magnetic field and the transformer, and in this video we are going to go into motor. So the notion that the phenomena of electricity and magnetism are interconnected, it was proposed first in the early of 1800s by H.T. Ørsted, a Danish physicist. So Ørsted showed that an electric current produces magnetic effects, or more specifically, a magnetic field. Soon after that, the French scientist André-Marie Ampère expressed this relationship by means of a precise formulation, and the formulation is known as Ampere's law. And a few years later, the English scientist Faraday, which we have been discussing in our previous topic about the induction law using the Faraday's induction law, he illustrated that how the converse of Ampere's law also holds true, that is, that a magnetic field can generate an electric field. Or in short, Faraday's law stated that a changing magnetic fields are going to give rise to a voltage. So we are going to undertake much details on the Faraday's law in this video. And as will be explained in the next chapter, the magnetic field forms a very necessary connection between electrical and mechanical energy. Ampere's and Faraday's law are going to formally illustrate the relationship between electric and magnetic fields, but it should already be obvious and evident from your own experience that the magnetic field can also convert magnetic energy to mechanical energy. For example, lifting a piece of iron with a magnet. In effect, the devices we commonly refer to as electromechanical should more properly be referred to as electromagnetomechanical, since they almost invariably operate through a conversion from electrical to mechanical energy, or vice versa, by means of the magnetic field. So Faraday effect stated that magnets plus a copper wire plus a motion are going to produce electricity. So we have in our previous lesson, the basic concept of electricity is given by we have the voltage V, which is the potential to move charge. We have the current I, which is the charge movement given in amperes or amps. And we have resistance R, which is from the Ohm's law, is equal to IR, where R is in ohms. And we also have power P, which is given in watts, or defined by equation IV, or equal to I square R. Some of the quantities that are going to be used in the magnetic field and Faraday's law are going to be the quantities that used to quantify the strength of a magnetic field, which is the magnetic flux, or known as phi, and the units are going to be Webers, WB. And then we have the magnetic flux density given by capital B in units of Webers per square meter, or Teslas. And the latter quantity, as well as the associated magnetic field intensity H, is in units of amperes per meter, or A over M, are vectors. So magnetic flux density and magnetic flux intensity are both vectors. So first we have the electric motor. Okay, in this figure we already seen this kind of motor everywhere in our daily life. So basically an electric motor are going to convert electrical energy to a mechanical energy. Okay, and in the motor it will consist of a permanent magnet and electromagnet. Then we have an electric generator, which basically or fundamentally have the same structure or components, but an electric generator are going to convert a mechanical energy to electrical into an electrical energy. So magnetic force on a current carrying conductor. The magnetic force is equal to the product of its length within the field of the magnetic field and the current I in the conductor, the external magnetic field B, and the sine of the angle between the conductor and the magnetic field. Or in short, the force, magnetic force F is equal to B, the magnetic field, or the magnetic field density, times I, the current, times L, the length within the field, times sine theta, the angle between the conductor and the magnetic field. So magnetic field are generated by electric charge in motion. So and their effects is measured by the force that they exert on a moving charge. And as you may recall from previous physics courses, the vector force F exerted on a charge of q moving at velocity of u, okay, charge q, velocity of u, in the presence of a magnetic field with the flux density of b, okay, is basically the product of all the three quantities, where symbol x are going to be used to represent that B is a vector cross product. So if the charge is moving at a velocity u in a direction that makes an angle theta with the magnetic field, then the magnitude of the force can be rewritten into F equal to charge, velocity, the flux density times sine theta. So can you relate between these two equations? F equal to BIL sine theta and F equal to QUB sine theta. So obviously the angle is the same. We have B, the density, and IL and QU is basically the same quantity. So if the angle is perpendicular, then sine theta are going to be equal to 1. We are going to get the magnetic force F equal to BIL. Before we proceed, okay, let's discuss a little bit on the magnetic flux or phi. So magnetic flux, or also known as phi or phi b, is defined as the integral of the flux density over some surface area. For the simplified, but it is also often useful, simplified case of magnetic flux lines perpendicular to a cross-sectional area A, we can see that the flux is given by the following integral, where phi is equal to integration of area A, density, flux density B, dA. So we can imagine that we have a figure where the force, and then we have the velocity u, okay, at an angle of theta, and then we have the magnetic field is B in this direction, and we also have the charge Q. Okay, and we can imagine that the magnetic flux lines crossing a surface are going to look like this, where we have a surface of A, and the magnetic flux is flowing through this surface, where we can define the magnetic flux as B integration of B over the area A. Furthermore, if the flux were to be uniform over the cross-sectional area, where we are going basically to simplify the area A, the preceding integral could be approximated by phi equal to BA, and the units are going to be in Weber. And basically, Faraday's law stated that if the imaginary surface A were bounded by a conductor, for example, a thin wire, then a changing magnetic field are going to induce a voltage and therefore a current in the conductor. So more precisely, Faraday's law states that at a time varying flux cause an induced electromotive force or EMF, or given as follow equation. So we have EMF or electromotive force. E is given by negative d magnetic flux over time. So that's it for a little discussion on the magnetic flux and the magnetic force and its relationship with other quantities like electron charges, velocity, and the magnetic field density. Next, we have a torque for a multi-turn coil, and the formula is given by T equal to K B I W sine alpha, where K is the constant depending on the coil geometry. B is the magnetic flux that we have discussed earlier. IW is the current in the wire, and sine alpha is the angle between the magnetic flux density B and the normal to the plane of the coil. So the angle in between that two. So when a current carrying conductor is placed in a magnetic field, there is an interaction between the magnetic field produced by the current and the permanent field, and this is going to lead to a force being experienced by the conductor. The magnitude of the force on the conductor depends on the magnitude of the current which it carries. So the force is maximum when the current flow perpendicular to the field, as shown in the diagram A. Okay, we have the current is in perpendicular direction to the magnetic field. Therefore, we are going to have the electromotive force F max. And the force are going to be 0 when it flows parallel to the field as in diagram B. So when it is in parallel direction, there will be no opposite or acting forces acting on that conductor. So the force are going to be 0. Using the Fleming's left hand rule, we can easily determine the direction of the force, okay, that was induced by the changes of the magnetic field. So basically, you just need to use your left hand, your thumb, your index finger or your forefinger, and your second finger. So your thumb are going to be the direction of the thrust or the force. So T for thumb for thrust or force. F, your forefingers or your index finger are going to show the direction of the magnetic field, or B, okay, the magnetic field. And C, the second finger, are going to show the direction of the current through the conductor. Can be wire or anything. Okay, so you can use Fleming's left hand rule to understand the direction of the force, the magnetic field, and the current. So now let's try using the Fleming's left hand rules in this diagram. So we have the force is acting toward us, and then we have the magnetic field is pointing downward, so you can use your forefinger to point downward, and then the current is pointing to the left, so you can put your second finger to the left and check either you have the direction of the force similar to the diagram here. Now we have we want to create a motor, and using electromagnet and permanent magnet and our understanding of Faraday's law, okay, a DC motor which consists of armature, brushes, commutator, permanent magnet, electromagnet, coil, and some other part. So looking at this example of motor, okay, we can check the direction of the force that's going to be acting towards this armature. So we have the currents is flowing in this direction, and we know that the magnetic field of two permanent magnets are going to be from north to south, okay, from north to south. So we have the direction of current here, so we can use the Fleming's left hand rules, and we are going to see that the force are going to be acting upward for the left part of the armature, while the right part of the armature, the force are going to be acting downward, and therefore we are going to have a circular motion or a rotation of this armature. Okay, and this circular motion are going to be very useful in making motor. So in a vertical position, okay, the armature will be in this position uh, where it will continuously spin, and I'm going to explain on the basics of motor in the next slide. An electric motor basically consists of electromagnet and permanent magnet. So electric motor is all about magnets and magnetism, okay, where we use a magnetic field to create motion. So the characteristic of magnets, where the opposites are going to attract and the same pole are going to repel, are going to be used in the foundation of electric motor. So these forces of attracting and repelling are going to create a rotational motion, which we have looked a little bit in the previous slide. And basically a motor are going to consist of two magnets, okay, a permanent magnets on both sides and an electromagnet in the middle. So let's take a look at parts of the motor. So we have armature or the rotor, we have commutator, we have brushes, and we have axle and field magnet. And of course, we also need a DC power supply or some sort of power supply. So in this figure, we can see a construction of a motor, where you can see we have the permanent magnet at the side of the or the case of the motor, and then in the middle we have the electromagnet, which consists of coils of armature, and these coils are connected to a shaft, okay, that's going to transmit the rotation. So this is a motor illustration from a simplified version where we have the permanent magnet and we have the electromagnet in the middles with armature, okay, and then we have brush which is in contact with the commutator, okay, and the brushes are connected to a DC power supply, okay, it can be a battery or whatsoever, and we are going to have a rotation of this armature in this direction. So first let's take a look at the armature. So the armature is an electromagnet made by coiling thin wire around two or more poles of metal core. The armature has an axle and the commutator is attached to that axle. Okay, so this is the axle. Okay, and it is attached to the commutator. When you run electricity into this electromagnet, it creates a magnetic field in the armature that's going to attract and repel the magnet in the stator, okay, at the side of the motor, so that the armature are going to spin through 180 degrees. And to keep it spinning, okay, you are going to have to change the poles of the electromagnet. And then we have commutator and brushes. The commutator is simply a pair of plates attached to the axle. So this is the commutator. And these plates provide the two connections for the coil of the electromagnet. Commutator and brushes work together to let the current flow to the electromagnet and also to flip the direction that the electrons are flowing at just the right moment or at the right angle. So the contacts of the commutator are attached to the axle of the electromagnet. So they spin with the magnet, and we have the last part, we have the brushes here, the red one, and where the function is just to make contact with the commutator. So brushes is just a two piece of metals attached to a spring or carbon, and it will connect the commutator with the power supply. So this is an image of spinning armature. So if you can see, the commutator and the armature is in one rigid body, is one connected body where it's going to spin, and the brush are basically going to uh, stay in contact with the commutator. So this is an example of motor. So previously we have an example where we only have an armature with two axle, but in this example you can see we have four permanent magnets surrounding the electromagnet in the middles, where the electromagnet is connected, or the number of armature that we have, okay, means that we are going to have less loss of motion during the rotation of the commutator. Next, we have the torque speed curve. So in order to effectively design DC motors, it is necessary to understand the characteristic curve. So for every motor out there in the market, okay, there is a specific torque speed curve and power curve. So we have, for example, in this figure, we have the torque and the rotational speed. So the curve is given by a straight line, okay, where at the stall torque, tau s, we have the motor is not spinning or stalled, okay, where the speed is 0, the torque is maximum, while at a maximum speed, okay, no load speed, so the torque is 0, but the maximum speed is maximum at omega n. So this graph shows that a torque speed curve of a typical DC motor, and we can easily note that the torque is inversely proportional to the speed of the output shaft. Or in other words, okay, there will be a trade-off between how much torque a motor delivers and how fast the motor can spin. So the stall torque tau s represent the point on the graph which the torque is maximum but the shaft is not rotating, speed is 0, and the no load speed omega n is the maximum output speed when no torque is applied or no load at motor. Next, we can also calculate the power of specific motor using the torque and speed curve. So at the location where the motor is not spinning, okay, we are going to have a low power of area by calculating the area under the torque and speed. And at rotational speed maximum, we also will have a low power, and the maximum power are going to be produced when the torque and the speed is approximately half from the maximum torque and half from the maximum speed. So this is where the maximum power of the motor can be obtained. So torque, power versus speed. So maximum output power occurs at the torque half of the stall torque and the speed half from the no load speed omega n. So we can see from this graph, okay, the maximum power occur here. So angular speed at the center or at the half from the maximum or no load speed. We can calculate the power of the motor based from the angular speed using this equation where it is equal to negative tau s stall torque over the no load speed times the speed square at the center 300 plus stall torque times the speed. We can also calculate using the torque using different equation but almost similar in this equation. Various losses are classified as follow. Okay, so a real motor will have some kind of energy loss, power loss. The first type of loss is caused by electrical, the copper loss in various windings such as the armature windings and the different field windings, and also the loss due to the contact resistance of the brush. So we learned that the brush and the commutator is in contact, so there will be an electrical losses in this part. There will be also magnetic losses where the iron losses are included, and the hysteresis and the eddy current losses in the various magnetic circuits. And this is going to occur primarily in the armature core and the pole phase. And then we also have the mechanical loss. Okay, once the electrical power is converted into mechanical energy, okay, there will be mechanical losses which includes the bearing friction, the windage, and also the brush commutator friction losses. And there will also be stray load, and these are other load losses that is not covered above. Basically, they are going to be taken as 1% from the output as a rule of thumb. So motor losses using direct current, okay, DC motor. So input power from electrical power. So this is a field copper loss between 1 to 5%, and then at the armature circuit copper, there will be another losses around 3 to 6%, okay, caused by the brush contact and the armature. And then we also have the mechanical part, the no load rotational loss. The rotational loss are going to be around 3 to 15%. The efficiency of DC motor, so similarly like the transformer, okay, we can calculate the motor's efficiency eta, and the mechanical output power is divided by the electrical input power. So for transformer, if you still remember, we have the power from the secondary over the power from the primary. So for motor, we are going to calculate the efficiency using the power of the mechanical output, which is the secondary part, and over the power of the electrical output, which is the primary part. So PE is the electrical input power and PM is the mechanical output power. So in a simplest case, we can calculate PE equal to VI, voltage time current, and PM we can calculate using T omega, where T is the top and omega is the angular velocity. So the power output motor P out is equal to T omega. So T is top and omega is the radian per second. We can use the quantity RPM, but we need to multiply by 2 pi/60. And then the power input can be calculated using the Z equation P equal to VI. So in order to increase the efficiency of DC motor, there are several methods that we can use. First, we can increase the number of turns in the coil. Okay, in the armature, okay, we can increase number of turns, use more coil, so means it will be much heavier. So there will be a give and take in that part. And then we can also increase the strength of the current. So we increase the value I, and then we increase the area of cross section of the coil. So this is also regarding the coil. And last one is we can increase the strength of the radial magnetic field. So we use much stronger permanent magnet and put it at the stator. So that's it for topic chapter 4. So we just finished transformers and motor. And don't forget to answer the practice in the slide note given. So that's it. Thank you very much. Assalamualaikum.